Hello everyone. Let's talk about VRMS. Root mean square speed or root mean square velocity. We have developed PV as 2 by 3E. This E is half m v square for n number of molecules or atoms. This v square is VRMS. And I already told you the meaning of RMS. How do we handle it? How do we read it? How do we solve it? Root means square. That's how you read it. SMR. That's how you solve it. So, for a given sample, when you write PV equals 2 by 3E, E is the internal energy, which is half mv square RMS, mass of an atom or a molecule, its RMS speed, square of that. There are n number of molecules, that gives us total kinetic energy. But we also say that energy per degree of freedom is half kT. This K is Boltzmann's constant. For a monatomic system, there are 3 degrees of freedom, and therefore energy is 3 by 2 kT. This is the energy of a single molecule. If there are n number of molecules, then that energy, which was called U, is nothing but E for us. This E or U, they both are what? Same. Energy per degree of freedom. A monatomic gas molecule has 3 translate-free degree of freedom. For simplicity, we'll talk about monatomic part only. 3 by 2 kT. There are n molecules present inside. That gives us E as 3 into kT by 2 multiplied by n. This is simple presentation of kinetic energy of mv square. Everybody knows that this is the kinetic energy. There are n molecules. So from this and this, we can find VRMS. You can see that n and n gets cancelled, half and half gets cancelled. What is VRMS coming? VRMS is coming root over 3 kT divided by m. Half cancelled, n cancelled. VRMS is coming what? Square root of 3 kT divided by m. M is mass of the molecule, T absolute temperature, K Boltzmann's constant. This is the VRMS square mean root If you calculate speed of a given molecule, go for its square, do the same with each and every molecule present in the sample, and then find the mean, and finally root, it will give you 3 kT divided by m. The important thing is that RMS speed has only one important part, that it relates temperature and speed, which was called or is called kinetic interpretation of temperature. Note down this much and then we'll write a few statements. Write down the heading: root means square, velocity or speed. Write down a statement: RMS speed of a gas molecule, RMS speed of a gas molecule is proportional to square root of absolute temperature, is proportional to square root of its temperature. Inside the bracket you can write kinetic interpretation of temperature. Kinetic interpretation of temperature. And is inversely proportional to square root of its mass. Is inversely proportional to square root of its mass. Now write down a question. In a cylinder, two non-interacting gases are present. Two non-interacting gases are present. They basically do not combine chemically, they don't make any bonds and all. Two non-interacting gases are present such that masses of their atoms are m1 and m2 respectively. In equilibrium, find out ratio of their kinetic energies. In equilibrium, find out ratio of their kinetic energies. Kinetic energy of the molecule. So you've got molecule of type 1, molecule of type 2. You have a thermal equilibrium. Thermal equilibrium means everywhere inside the sample temperature is what? Same. That is the meaning of thermal equilibrium. So everywhere your temperature is same. And question is, what is the ratio of K1 is to K2? We've got 20 seconds. Let's see how many of you will answer this. Good. Only 3 responses and all 3 are correct. लोग यहाँ भागते हैं. It's inversely proportional to m and all. But the thing is, look here. This E is kinetic energy. So if I go for half mv square, then half mv square, V is the average. Average means RMS type of average. So this half mv square is what? Is a function of K and T. Square. The whole thing is a function of temperature only. Speed is inversely proportional to m. What is kinetic energy? Kinetic energy is only what? Half kT. Energy is what? Half kT multiplied by degrees of freedom. There is no term of mass present. This is Boltzmann's constant, which is same for every gas. So once you say that kinetic energy is a function of temperature only, speed or RMS speed is a function of temperature as well as mass. I hope you understand this presentation. If you do not, then it means this thing is a function of T. This thing is a function of, that means it depends upon T as well as M. So since I'm asking you ratio of kinetic energy, which is a function of temperature, system is in equilibrium, and therefore ratio can only be 1:1. Note on this. Remember, we are talking about average. As I've told you that it is quite possible that if somebody looks at a given atom of type 1, if you go for a very powerful microscope and you can see an atom of M1 and a second atom of M2, another atom of M2, it is quite possible that it is at rest, whereas this one is moving. So you will say that no, one has no kinetic energy and two has got certain kinetic energy. You're not talking about these kinetic energies. You're talking about kinetic energy of the entire sample and then its average. So we are into that. And this ratio, it only depends on this kinetic energy, it only depends on what? T. So those of you who could not answer this, are you comfortable with this part? And everybody, even those who answered this thing, they must write that kinetic energy is a function of temperature. So if you are comfortable with all this, then write down yes in the comment box. Write down one more statement. So if you find VRMS, suppose you are interested in finding root mean square speed of air molecules in the room right now. So when you put all these values, this speed is roughly of the order of speed of sound, of the order. So speed of sound is roughly 332 meters per second. You'll find that these things are 400, 500, 300 meters per second. So a molecule, when it moves, it is moving with, I'm just giving you an approximate order. We can write that this is roughly the speed of sound in that particular medium, which is 332 meters per second. Normal situation, STP. It will depend on M of different molecules. It will depend on T. I'm just giving you the order. So write down the statement. It is observed that RMS speed of a gas molecule is of the order of speed of sound in that particular sample. Suppose you have a sample of helium. If you go for speed of helium molecules, RMS speed of helium molecules, then that will be of the order of speed of sound in that sample of helium gas. This creates a problem for us. If you say that a gas molecule is moving with a speed of 332 meters per second, in just 1 second, it can move 332 meters per second, meters in 1 second. That means if you have a molecule, and as we say that in an ideal gas, this one interacts with this then gets the energy of this one, and the whole thing continues. So in just 1 second, we can transfer information from this place to roughly a place which is at a distance of 332 meters. In other words, अगर हमने कहीं पर if we have a gas cloud present at one position, then this result or this information is suggesting that all the atoms or molecules of that gas cloud are moving with 332 meters per second, and therefore gas cloud can move very fast from one place to another. But that doesn't happen. It doesn't happen because when molecules collide with each other, it's not always in a real situation. It's not always a head-on collision. Most of the time it's an oblique collision. So whenever an oblique collision takes place, what is an oblique collision? I hope you remember. So whenever an oblique collision takes place, this molecule is moving in this direction, So whenever an oblique collision takes place, this molecule after the impact may move in this direction depending on the angle of collision. We have already done these things, you know where. So the thing in blue is after the collision. This one, let's say after the collision, it's moving in this direction. So all these molecules, they are moving and they always collide such that collision takes place in random directions. If you have a single molecule, just imagine hypothetically, if you have a single molecule, if you allow it to move, then it will definitely travel 332 meters. But in reality, it starts moving with 332 meters per second, collides, moves in this direction, suffers another collision, moves in this direction, moves in this direction, and therefore a molecule simply cannot travel this fast. They are traveling this fast, but remember, it doesn't tell you that they can travel this far. A more correct thing will be they cannot travel this far in just 1 second because of these collisions. And we have a term which is called mean free path. Everything is mean, average, everything. The mean free path means before collision, how much is the freedom with a molecule, what distance it can travel, before it suffers a collision. This, next time, this, next time, this. So if you find the average of all these, that will be called what? Mean free path. Not for this one, for all other molecules, go and take the average. Once you find the average, this mean free path is given by this formula. I'm giving you the formula without derivation. Nobody will ask you the derivation. If somebody is interested how come we arrive at this, you can always ask me after the class. I'll give you a slight presentation of this. L is the mean free path, which is not 332 meters, is 1 upon root 2 pi d square n, where d is this is your molecule, d is its diameter, n is number density, number of molecules per unit volume. Just wrote down this and then I'll explain a little bit about the concept of mean free path. But first note down this much. D is the diameter, N is number of molecules per unit volume, L is the mean distance a molecule can move before it collides with the other. Look here, a rough idea of the mean free path thing. This is a molecule. It's moving in this direction. If it is moving in this direction, then this is its direction of motion. Colors are just for your understanding. These two red molecules, I hope you can see the color. If you cannot, it doesn't matter. Same size. Blue, red, black, they all have same size. For the simplicity, let's say these three are at rest, although they are also moving. And since they are moving, you get the term of root 2. You will see this term of root 2 with clarity in 12th. And we'll find RMS type of things in alternating current. You will understand the origin of root 2 there. As of now, remember the formula. This is for your understanding. So this molecule, as it moves, it will collide with this. It lies in its path. This is the boundary condition. This is the boundary condition. So we say that this molecule can collide with all those who are present in a hypothetical cylinder of this size. It's a cylinder in red color. I hope it's visible now. So, as this molecule moves, it suffers interactions with other molecules. It collides with other molecules. So as it collides, we'll say that it will collide with the blue one, all those which lie in this region. You're talking about center to center distance. So any molecule whose center lies between these two red boundaries, the center. If you have a molecule whose center lies in the cylinder shown with this red figure, then this molecule will definitely interact with that other molecule, will always suffer a collision. If you go for mean distance which this molecule suffers, you find mean distance of this, for all, and then you find the average, then that average is 1 upon root 2 pi d square n. This is called mean free path. Just for your understanding, mostly it's a formula which you need to remember. D is this diameter. This is D, diameter of the molecule. You can draw this figure. The blue one is such that its center is over here. You can draw several others. As long as you have center inside these two, this will definitely interact. Put down this. Write down the statement. Mean free path is of the order of micrometers. Mean free path is of the order of micrometers. That is 332 meters. And we are saying that on an average, this molecule has a freedom of moving up to 10 to the power minus 6 meters. So since it's free to move only for 10 to the power minus 6, then suffers a collision, all the molecules, they basically confine themselves in a cloud, and therefore you always see clouds. So whenever you see clouds, or when you burn something, the smoke, when it rises, that smoke, it remains together most of the time. It starts to spread out the moment it interacts with the cold air, but most of the time all that smoke, all the smoke particles, they are interacting with each other continuously. They are traveling only for 10 to the power minus 6, and then they are changing their directions. So instead of a free path of 332 type, they are only moving for an average distance of roughly 10 to the power minus 6 meters. Important parts are what? Mean free path is inversely proportional to d square. So this figure will help you in understanding why this is d square. This d square pi is basically cross-sectional area. This is the cross-sectional area part multiplied by n. This is the area. This L becomes volume multiplied by n. It gives you what? Number of molecules per unit volume. That is your total number of molecules. So this you can remember, L is inversely proportional to square of the diameter. There is one last thing in this KTG, which is degree of freedom, and I've already given you the concept of degree of freedom of gases, monatomic, diatomic. Apart from gases, in kinetic theory of gases, we are mostly interested in gases only, but they also ask in schools and competitive examinations questions for degree of freedom of solid and their specific heat capacities. So let's talk about the degree of freedom and specific heat capacity of solids. Let me remove this thing first. Tell me first, you have a solid, a block of iron. All those iron atoms, what type of degree of freedom we are interested in? Degree of freedom, translatory motion. For diatomic gases, there were rotational part also, and there were vibrational modes also. If you talk about a solid, we're not talking about a gas. If you're talking about a solid, an iron atom in a solid block of iron, so what type of degree of freedom it will have? Translatory, rotational, or vibrational? What do you think? What's your understanding is? Write down in the comment box. What's your opinion? Good. You can only have what? Vibrational. And because of that vibration only, it does what? It conducts heat from one place to another. It's not a gas molecule which can move freely. It's a solid thing. And therefore, for solids, when you talk about degree of freedom, you are talking about only vibrational modes. And in vibrational modes, we say that there are 2 degrees of freedom. So you have something which is vibrating. Connect a string, when the whole thing oscillates, then oscillation has what? Kinetic energy, and that spring also has what? Potential energy. These two energies, they give us what? 2 degrees of freedom. So when we talk about a solid, its atom has 2 degrees of freedom. For 1 degree of freedom, everybody knows that energy is what? Half kT. For a given degree of freedom, energy is what? Half kT. If there are 2 degrees of freedom, energy is 2 into half kT. If there are n number of atoms, then total energy is 2 into half kT multiplied by n. This U is same as Q because W is 0. dQ du plus dW. This term dW, you know, is what? PdV. When you supply heat, definitely volume changes, but that change in volume is very much negligible, and therefore we'll simply say that this PdV is approximately what? 0. That tells us that U and Q, they both are what? Same. What is this? Since a solid, atom of a solid can only have vibrational degrees of freedom, for vibration we always take 2 degrees of freedom, one for kinetic energy part and the other one for potential energy part. For every degree of freedom, total energy is half kT. For 2 degrees of freedom, 2 into half kT. If there are n number of molecules present or atoms present, then total energy of all those atoms will be U, which is equal to heat supplied, because there is hardly any work involved. Note down this and then we'll write a statement. So write down the statement. For an atom, of a solid, translatory and rotational degrees of freedom, translational and rotational degrees of freedom are not present, as they are for a gas molecule, which is free to move. An atom of a solid An atom of a solid can only vibrate. An atom of a solid can only vibrate, and therefore it has 2 degrees of freedom. It has 2 degrees of freedom for a given axis. It has 2 degrees of freedom for a given axis. Inside the bracket, vibrational kinetic energy and vibrational potential energy. Vibrational kinetic energy and vibrational potential energy. Now, so we have got, this is the atom, it is oscillating this way, or take a pair, the pair is oscillating. So as it oscillates, it has 2 degrees of freedom for a given axis, this. But you can always have this axis. You can always have this axis. So how many axes are present? 3. If there are 3 axes present, then this energy is supplied along a given axis. On an average, there are 3 axes present, X, Y, and Z. X, Y, and Z. Since there are 3 axes present, the molecules can vibrate this way. It can also vibrate this way. It can also vibrate this way. And therefore, this is energy of a given molecule for a given axis. It can also vibrate this way. But this has already X, Y, and Z present in it. And therefore, we are not interested in all the possibilities. We are splitting all the possibilities along X, along Y, and along Z axis. So, for a given axis, you can write U for a given axis. U for a given axis is what? Half kT multiplied by 2. There are 3, and therefore total internal energy, this is U for a given axis. U total for X, Y, and Z will be 3 times kT multiplied by N. kT multiplied by N. Now, we are interested in molar specific heat capacity of solids. What is molar specific heat capacity? Amount of energy supplied per unit moles per unit change in temperature. Per unit change in temperature. That's how we define what? We define molar specific heat capacity C. Heat supplied per unit mole per unit change in temperature. This dq, you can write after integration, we can also write like q. You take q or you write dq or you write delta q. As of now they are same for us. Integration of dq is going to give us q. So this dq upon n dt. This dq is nothing but u. Total u is 3 kTn. What is n? Number of atoms. N is number of atoms. What is n? number of moles. So this way we can multiply first of all dq as 3 kT into n, keep looking, 3 kTn divided by n. What is n? Number of molecules, number of moles. This number of moles into dt. This dt, I'm writing this dt now as what? T. This T and this T, they both are what? Same. How come they are same? Half kT. Temperature is raised from 0 to T. Temperature is raised from 0 to T. It becomes T. This is also what? T. This N into T is then, T is gone. T is gone. What is N? N is N multiplied by Na. How many molecules are present in N moles? N, number of moles multiplied by Avogadro number. This becomes 3K multiplied by Na. Boltzmann's constant multiplied by Na is the gas constant. Gas constant. We are dealing with solids. But this kinetic theory of gases can also give us an idea of molar specific heat capacity of solids. The concept of R is basically for gases, but it can also be used to define molar specific heat capacity of a solid, which is coming what? 3R. This 3R, you can see, has nothing to do with type of solid. So for all solids, not basically for all, there are exceptions present, but for us, for almost all solids, molar specific heat capacity is what? 3R. Whereas for gases, if you remember, molar specific heat capacity, it was different, and then it was also based on the type. At constant volume, different thing. At constant pressure, different thing. Monatomic, different thing. Diatomic, different thing. Diatomic with vibration, that was also different. But for solids, your molar specific heat capacity is coming a constant, which is 3R. Wrote down this. And then I will further explain this dt and t, because maybe you get confused with this dq and dt. But there should not be any confusion. Look here, we can always do something like this. dq is nc dt. We had defined molar specific heat capacity like this. Amount of heat supplied per unit mole per unit change. So I can always write this. If I integrate, what is the integration of dq? Q. N is a constant. C is a constant. So what is the integration of dt? T. So that's what I have done. This is dq. This dq is basically q after integration, and dt after integration is t. This q is coming 3 ktn. Q, u is q because there is no w, which is 3 ktn. 3 ktn divided by dt, which upon integration is now t. So I hope this dt becoming t is clear. Many times people get confused. So this is dq, this is dt. you're using dq as q, dt as t. So tried to save time but could not save it. Ultimately I had to explain everything. This dq and dt, when you're using it, you're basically using this fast integration. N is a constant, C is a constant. This is dy whose integration is y. This is dx whose integration is x. So I could have easily written C as q upon nt. I could have, but since I have only told you formula of C in this form, I wrote dq directly and this dt also directly as t. I hope this thing is clear. Is it? Yes or no? Now, write down first specific heat capacity of water. Last thing, specific heat capacity of water. Basically, the kinetic theory of gases is good for ideal gases only. What is an ideal gas? In which there is very large separation between the molecules, but we are crossing limits. We are using the concept for solids, for liquids, and it's just that the values are coming close. They are not very big variations. We are trying to use concept of KDG, kinetic theory of gases, for solids as well as for liquids, but more fundamentally we do not do this. In 11th we can do this type of trick. This is basically a trick. The assumptions of ideal gases are for gases which have no interaction between the molecules. Solids, they have so much interaction between the molecules that they cannot move freely. They can only vibrate, but still we are crossing the limits just so that you get an understanding of the whole idea. If somebody has to find molar specific heat capacity of a solid, then he has to go through each and every small variation. You will also need to include concept of change in volume. That too will be present. Contribution of temperature, concept of every molecule, its oscillation, its rotation, its quantum nature will be present. So we are doing what? We are just just don't mind joking around कि हमने gases के लिए develop किया है और solids and liquids पर भी कर रहे हैं. These values, they simply match. Many times they do not match. When they do not match, we go for quantum physics. आपके काम की नहीं है अभी. For water, you see, total energy of an atom is coming what? 3 kT. If you take n molecules, n times. For 1, 3 kT. H2O is what? HHO. There are 3. So we say that U will be 9 kT. Again, fundamentally, just link बनता जा रहा था. Values finally, the experimental observation and the observations coming from kinetic KDG, they are all matching up, and therefore we study these things, but more fundamentally we do not use these things. We use these concepts only in 11th. In advanced physics, बकवास है सब ये. फिर भी अपने काम का है, इसलिए देखते हैं. This U is 9 kT. How come? H2O, HHO. If it were correct always, then we could have used the concept for anything. We don't do that. We don't do that. Only for water and some other things it works out like this, and therefore it is taught. So, for an atom, we found that 3 kT. Whose atom is this? This was an atom of a solid. This is an atom of a liquid. But liquid at rest in a beaker is just like a solid. Basically, it is not. Those atoms are also moving. But again, the approximation. So, for 1 degree of freedom, half kT, there were 2 degrees of freedom along one axis, 2 into half kT. There were 3 axes, gave us 3 kT for an atom. There are 3 atoms, and therefore we are saying there are 3 into 3 kT giving us 9 kT. To save time, when this is 3 kT, your molar specific heat capacity is coming 3R. Do the same thing. 3, replace it with 9, divide by NT. Do the same thing with water. Simply replace 3 with 9 and you get your molar specific heat capacity, which is 9R. When this 9R is used for 1 gram of water and temperature is raised by 1 degree Celsius, it comes close to 1 calorie. And I hope you remember that specific heat capacity of water was 1 calorie per gram per degree Celsius. Just so that this is in good agreement with this, it is taught. But this type of working is not always correct. So, for water, simply do what? 3. If you have some other molecule, let's say CS3COOH, can we do that? No, we cannot. It's not that you could simply multiply number of atoms with 3 and you will get the specific heat capacity. No, that doesn't happen. But it works for this and therefore it is taught. C is coming 9R. This is what you need to remember. What is molar specific heat capacity of water? 9R. What is molar specific heat capacity of a solid? 3R, because of this 3. Note down this.